All right, so I'm gonna just solve some problems, explain my logic as I'm solving them, and hopefully this will help you guys figure out something. Ideally, this video should be used as like a tool to help take the notes and the content we've been talking about and doing and applying it to the problems and learning how to pick out the important words and stuff like that. You know, just in general, trying to make you successful. That's the plan. You should be good at life, and I want to make you good at life. So let's be good at life. So most of these are from past IB questions or exams, or I might have made one or two of them up just because I couldn't find a good question, or else the questions were worded too long for me to fit on a PowerPoint slide. So this is one off of an old exam. Um, so isotopes of an element differ in their atomic number, number of neutrons, position on the periodic table, and um, electron arrangement. What this is really hinting at is, do you know the difference between these three things? Atoms, ions, and isotopes. Atoms are, these are just neutral, meaning protons equals electrons. Ions, it's all that's implying is that protons do not equal electrons. These could be anions or cations. Remember, anions are negative, so they have more electrons. Cations are positive, so they have more protons. Isotopes of the same element, this is when you have two atoms. Technically, they could be ions as well, but IB doesn't really venture down that road too much. But two atoms of the same element, but with different masses, different mass numbers. So if you have something that differs in atomic number, so I'm examining A here, if you have different atomic numbers, then you would have different elements. Because if you have different atomic numbers, that means you have different protons, and since elements are decided by the number of protons they have, then they have to be different elements. And since we said isotopes of an element, that means there should only really be one element that we are discussing here, whatever element that may be. And since if we're changing the atomic number, we're changing the elements, it's for sure not A. B is going to actually be the right answer. I'm going to explain why C and D are not correct first, though. All right, so then let's just jump down to C. If they have a different position in the periodic table, that implies that they have a different number, atomic number. Because the periodic table is designed by increasing atomic number. So hydrogen's 1, helium has an atomic number of 2, and so on and so forth. So if they have a different position in the periodic table, that means the atomic number is different, which means a different element. We already talked about that and why A is wrong. So it's for sure not C. If something has a different electron arrangement, what that means is there are either more or less electrons. That's not necessarily true 100% of the time. For right now, we're going to just go with it. What that really means is if there are more or less electrons, and if it's an element, that means the protons should be the same. That would imply then that if they have a different electron arrangement, that means these are ions and not isotopes. Or sorry, inherently, this answer doesn't mean they are isotopes, so it's not D either. If you have different number of neutrons, that doesn't impact or it doesn't have an effect on the number of protons or electrons that element would have. The only thing this would impact, if you change the number of neutrons, is this would change the mass number. of whatever we are talking about, which is exactly what we're trying to get to with an isotope. Remember, this is just different masses. So because of that, B is actually our right answer. The rest of these, A, C, and D, are indirectly referring to the number of protons or electrons and not the number of neutrons. Electron configuration. An element has the electron configuration 2, 7. In other words, we could write this as 1s2, 2s2, 2p5. That looks like a 6. 2p5. This doesn't actually help us solve the problem at all. This is just Mr. Parks doing teacher things and forcing in review wherever he can possibly cram it into. So, what would be the electron configuration of an element with similar chemical properties? Chemical properties. That's really just describing how it reacts. And the way things react is really based on what kind of ions they're going to form, what are like the most common oxidation states, and things along those lines. So since we're talking about ions and similar chemical properties, that's really just saying which one of these is going to have similar valence electrons. The valence electrons are the number of valence electrons something has is going to have a significant impact on the chemical properties that something has. In the next chapter, we'll talk about other factors that impact chemical properties. But for chapter 2, we're really just focusing on the valence electrons. This is the same reason why if you got a periodic table and it looks like this, and this is a bad one, and let's say we have the halogens here and the noble gases. These two columns, if you have elements that are in the same column, they behave similarly to other elements within that same column, that same group. And that's just because they have the same number of valence electrons. So what I'm looking for here is really just any answer that has 7 valence electrons. If they gave us this kind of electron configuration, I would just be looking at my valence shell, which is the second shell, and adding up the total number of electrons, which would be 7 valence electrons. So then I'm going to just find the answer that has 7 valence electrons. And then that'll be this guy right here. Answers we can rule out immediately just by looking at this is C. The reason why C is not a good answer is because based on the electron configuration that they gave, this 271, that electron configuration is implying that the second energy level would not fill completely before I got to erase my X. That would imply that this level is not filled, but this electron is at a higher energy level. The only way this could have possibly occurred is if this electron was excited and for a split second in time was at a higher unstable energy state. That's the only way C could have possibly existed. And even then, you wouldn't write that configuration like that. Instead, it would be like an N from state 2 to state 4 or something like that. We'll have one of those questions coming up. But that is not the case, and this is a violation of the Aufbau principle, the building up. So D is our answer here. Spectra fundamentals. An emission spectra consists of a series of bright lines that converge at high frequencies. Such emission, such, such emission spectra provide evidence that electrons are moving from blah, 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 blah. Whenever you see answers like this, where the answers are long, I would encourage you to just take a minute, answer the question in the way that you know is correct, maybe by just making quick side notes off to the side, like quick or tiny notes off to the side, and then take what you know is correct and find which answer fits that. So what I'm going to do is break this down into important parts. So emission spectra. That means that we have an excited electron falling down to its ground state and emitting that photon of light. Okay? And they are going to converge, which just means get closer together. So these lines are converging at the top. They're getting closer together at high frequencies. This is going to be the trick here. High frequencies. When our nu is high. Such emission spectra provide evidence that electrons are moving from talk, bunch of answers. If they are converging at high frequencies, that is implying that E is equal to h nu. So as the frequencies go up, the energy is going up. So therefore, as energy levels are increasing, these lines are converging. So what we're looking for is that as the energy goes up, the energy levels must be getting closer together. They're converging like we have up here. So we're looking at probably from lower energy levels to higher energy levels. The higher energy levels are getting closer. All right. So what I want to do now is I'm going to reread the question because this is a confusing one. And I'm going to make sure that my answer in my head is going to, first of all, make sense, and then I'm not going to get tricked on one of these lengthy multiple choice answers that they're giving me. So I would for sure be taking a lot of time on this question, not because I don't understand what it's asking me, because I do, but more because I don't want to get tripped up because I misread it. So I would be going really slowly through this question because there's just a lot of words and jargon, and by about this time you know how well I spell and read, and I'm just not good at either of those things. So the emission spectra consists of a series of bright lines that converge at higher frequencies. Such emission spectra provide evidence that electrons are moving from higher energy levels to lower energy levels. For sure that, because in order to emit, we need to go from high to low. So from higher energy levels to lower energy levels. So these would both be absorption, because that electron would be taking in energy, it would be absorbing energy. And I'm pretty sure I spelled absorption wrong because I always spell that word wrong. So it's got to be C or D, and then with higher energy levels being closer together, and that's coming from this logic I provided right there. So D would end up being my answer. It's going from higher to lower because it's emission spectra. It's sending out energy, so it has to be falling down. That the particle, whatever energy that particle loses, is emitted in the form of a photon. And then they're telling us it's converging at higher energy levels, so the higher energy levels must be closer together. The difference in those bits of energy, those discrete quanta of energy, are smaller and smaller. Understanding mass spectroscopy. What's a good way to say this? This is a question that you can just have down by rote memorization. I would encourage you not to, because if you can logic through this, it does make sense. I would encourage you guys to think about everything in chemistry in terms of magnets, varying strengths of magnets. So if you have like aluminum 3+, that's a really strong magnet compared to like a sodium 1+, that's a pretty strong magnet. And then eventually we'll get into like nonpolar and polar things, which are very, very weak magnets. These particles act in terms of magnets. So the way mass spectroscopy works, and I'm going to draw a very crude picture here. Whoop. I'm going to divvy it up into sections. So first you put in your sample, whatever it is you're looking at, and it's going to be in whatever state it's at room temperature, because you would have it at room temperature. And then in this first little compartment here, the sample will get vaporized. In other words, it just turns into a gas. To say it turns into a gas makes it sound like it's spontaneous, like you put it in this box and all of a sudden, poof, it's a gas. That's not the way. Either it's going to be at incredibly low pressures or high temperatures. We turn it into a gas. We vaporize it. The next thing we do in this other container, it'll move on, and then here it's going to ionize. What we do then is we basically bombard it with particles until we knock off an electron, a single electron, just one. Because the second it becomes ionized, there is a magnetic field. You'll see magnets, and you're starting to catch the idea. And the magnetic field is going to be applied, and it's going to pull particles this way out of the ionization chamber. So when it becomes ionized, this will turn into a cation. The second it becomes a cation, the magnetic field can now act upon it, because if it's neutral, the magnetic field will not act upon it, because there's nothing for the magnetic field to act upon. Magnetic fields act upon charged particles. The second it ionizes, that magnetic field is going to pull it off to the side. It's going to, in other words, it's going to accelerate. It's going to accelerate it down this tube. And then it'll get into this final little chamber. And then the same logic is going to be applied. We're going to have another magnetic field. I'm going to do this in a different color. And that other magnetic field is going to be pushing it perpendicular to the previous magnetic field. The idea is that the velocity that the particle has when it enters this final chamber, so this particle will have a this thing will have a velocity, and then as it continues its trajectory, the magnetic field will start to work its magic and slightly pull it one way or another. If it's a light particle, it's going to deflect a lot. Think about it as if I'm pushing a child on a swing, if the child is light, I can push him or her very far. But if the child is bigger and heavier, imagine I'm pushing a year 13 kid on a swing, I'm not going to be able to push him as high immediately. So this magnetic field will begin to deflect the ion. And the curvature of the deflection is going to be dependent on the mass of the particle. So this would be the cyan one would be a heavier particle, whereas this red one would be a lighter. I know heavier and lighter are not the correct terms. It should be more massive and less massive, but just go with it. And then this final wall here, ooh, I'm running out of colors. This final wall here is just the detection point, where each individual, wherever a particle hits, is going to have a it's going to trigger a response in the machine, and it's going to say, okay, I had a particle hit right here. And if a particle hits at that spot, then it has a mass to charge ratio of this. And that's how we're able to determine within a specific sample what the mass of certain particles are based on how much they deflect in this the deflection chamber. So then the pattern is you first vaporize, then ionize, then you're going to accelerate, you're going to deflect it, and then finally you're going to detect. So we're looking for vaporize, ionize, accelerate, deflection, detection. C. If you need to, and this logic doesn't make sense, I would strongly encourage you to come talk to me and I'll explain it and we can draw pictures and do whatever that is that you need to understand it. Or you can just do route memorization. I'm never going to advocate for route memorization though. Okay, which of the following contains 19 neutrons, 17 protons, 18 electrons? So if I'm doing this, I look at this immediately. 17 protons, 18 electrons. So then whatever species it is, it's an anion because there's one more electron than protons. Therefore, since there's one more electron, it should be anionic, which lets me immediately get rid of these two options. Those are cations, for sure not right. So then I'm really down to chlorine 36 or potassium 36. The 36 is just telling us the mass number. In other words, it should be protons plus neutrons, which makes sense because I got 19 neutrons, 17 protons. If you add those up, you should get 36. If you're not getting 36, you're probably not using your calculator right. If you're using your calculator, then you're not doing paper 1 right, so you shouldn't be using your calculator either way. So anyways, I'm going to just look for whatever element now has 17 protons. If something has 17 protons, that means the atomic number is also going to be 17, which means I know the element, which means I know it is chlorine. Ta-da! Oh, this is a fun one. I really like this one. Okay, so a sample of an element was analyzed using a mass spectrometer. Remember, mass spectrometer, it's going to deflect things based on their mass to charge ratio. Two common isotopes were found with masses of 35 and 37. So basically what you can imagine is they have a set of an element, and then they ran it through a mass spec, and then from that they found out that 10% of the sample was comprised of isotopes with mass of 35, just a little bit, and this is going to, these guys will weigh 35, and 90% of it weighed 37. Most of it, I don't like that. It doesn't look like a nice little shape. Let's make it look prettier. Most of this being 37. What is the relative atomic mass of the sample? Some of you guys might be panicking and you're starting to do math. Don't do math. Read the answers first. So our answers are 35, 37, in between 35 and 36, and in between 36 and 37. I'm going to start to do this problem as if we were going to do math, just to help you guys remember. The best way to do this is pretend like you just have 100 atoms of this stuff. So if you had 100 atoms, your relative atomic mass would be, it's really just an average. So you'd have the ones that weighed 35 and there was 10% of them, and then the ones that weighed 37 and there was, how much of it? 90% of them. And then you could do the math from here if you really wanted. A much easier way to do this would be if it's just an average. And since the vast majority of this is 37, but there is some 35, that means the average is going to be very close to 37, but a little bit below that because the particles that weigh 35 are going to lower that average. So it's going to be close to 37, but not quite. So it's for sure not 35 because we have some that are 37 in there, some that have a mass of 37. Same logic, it's for sure not 37 because we have some particles that weigh 35 in there. And then really these two are just asking you, is the average closer to 35 or 37? It's closer to 37. A particle has an electron configuration of 1s2, 2s2, 2p3. First and foremost, this is about as vague as they could possibly be. This could be an atom or an ion. You don't know anything about it. The only thing we know is that this has 5 electrons in total. I've got the 2 in the first level, the 2 from the 2s, and the 3. Oh man, that's for sure not 5. And 7. See, I struggle with math too. 7 electrons. And I'm getting these numbers from the exponents. So there's 2 in the 1s orbital, there are 2 electrons in the 2s orbital, and then there are 3 electrons in the 2p orbital, and those would all be spread out. So in total there are 7 electrons. So then what we need to figure out is which one of these 4 answers is going to have 7 electrons in there. Carbon has an atomic number of 6, and boron has an atomic number of 5, meaning boron would start with 5 electrons in its elemental state. And in order for it to get to 7 electrons, which is what we're looking, it would need to be B2 minus. It would need to gain 2 more electrons. And I'm not seeing B2 minus on any of my answers. For carbon, it's going to start with 6 electrons. So it really just needs to be a carbon anion, which I am seeing right up there in A. It's just how many electrons do these things need to gain to get to the 7 that this electron configuration is showing you. Electron orbitals. This is a really fun question. How many p orbitals have 1 or more electrons occupying them in the element germanium? We are going to assume elemental. Oh God. I can save this. Elemental. Nice save, Mr. Parks. Thanks, guys. So nice to me. Therefore, neutral. I don't even have the location of germanium memorized in my mind. So what I'm going to do is dig out a periodic table. Because your periodic table is your best friend in the whole wide world. So I'm going to pause this while I find germanium on the periodic table. Okay, I found it. And it's number 32. I'm going to solve this the long way because it's worth it. And the longest way to do this is going to be via orbital diagrams. 1s, 2s, 2p, 3s, 3p, 4s, oh God, 3d, 4p, 1, 2, 3, 1, 2, 3, 4, 5, 1, 1, 1, 1, 1, 2, 3, 1, 2, 3. I'm breaking a lot of rules that I'm going to insist you follow when you're drawing your orbital diagrams, and that's just for the sake of speeding this up. What are we in? We are in 4p2. All right, I'm going to take the time to count up my total electrons to make sure that they all are there. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 32. Cool, so all my electrons are present and accounted for. So then now, how many p orbitals have one or more electrons occupying them? I'm going to just count them off in red. 1, 2, because those are separate p orbitals. One would be the px and one would be the py. There are also p orbitals on the third energy level and the second energy level that need accounting for as well. 1, 2, 3, 4, 5, 6, 7, 8. So in total, there are 8 p orbitals. 3 of them in the second energy level, 3 of them in the third energy level, and then 2 more in the 4p. 1, 2. In total, 8 total p orbitals have electrons in them. Oh, here we go. Atomic emission spectra. Which transition would emit a wavelength of light in the visible region? This is a pretty poor question because they would have to specify with Bohr hydrogen model. Excuse the poor handwriting. I'm just being nitpicky with the question right now. Let's go ahead and draw these electronic transitions. Ground state. 2, 3, 4, 5. And they get closer and closer and closer. So key phrases that key words. Emit. That means we are going to have an electron going from excited to a lower state. It doesn't necessarily need to be a ground state. And the reason why I say this is because this is the next key thing we're looking for, the visible region. Can we see this? Whenever you see visible region, that means whatever the transition is, it needs to end at the second energy level. And the reason being is the transition from 2 to 1, since we're closer to the nucleus, the energy difference is larger. The change in energy is going to be greater, and since that's going to be greater, that means the frequency is also going to be, change in energy is going to be higher. That means the frequency is going to be higher, and it's so high that it actually gets into the ultraviolet range. And we aren't able to see that. So we're looking for something that is going to end at 2. So it's going to start at a higher state, and it's going to drop to n equals 2 because it needs to emit. So then I'm seeing this one ends at 2 and this one starts at 2. This would be an absorption because this electron would be going up an energy level. It would have to absorb some sort of energy. So because it's an emission spectra, it's emitting a wavelength, it's releasing this energy, C is going to be the correct answer here. If they asked for something, what would emit a wavelength in the ultraviolet range, then you would be looking for something dropping down to 1. And if they asked for something in the infrared range, then it's going to only drop down to n equals 3. We'll talk about that later. Oh, preview of chapter 3. You can logic through this too. A lot of chemistry is just logic. So, which of the following species will have the smallest radius? Mg2 plus, Na plus, F minus, O2 minus. These all, I'm checking the periodic table, these all have the same electron config. And they're all going to have the same configuration as neon. In other words, they're all going to have a 1s2, 2s2, 2p6 configuration. So, correct? Correct. So they're all going to have the same electron configuration. And if something is going to be a small radius, what that means is the electrons around that species, that nucleus, are going to be pulled in much tighter than the other options. And since electrons are negative, protons are going to be able to pull those electrons in tighter. So this is really just a fancy way of asking which one of these four options has the most protons, seeing as the amount of electrons are equal for all four of them. So fluorine's got 9 protons, oxygen has 8 protons, sodium has 11 protons, and magnesium has 12 protons. Since the ratio of protons to electrons is the greatest in magnesium, this will have the smallest radius. There are 12 protons, and those 12 protons are able to pull on those 10 electrons much more strongly, with much more force than the other 3 options. And then in this situation, O2 minus would actually have the largest radius because it has the least amount of protons, and then those electrons would be able to repel themselves more. This is a preview of Chapter 3. It should not be on the Chapter 2 test, but it is worth getting into this mode of being able to logic through something. Ideally, this is why I'm an advocate against route memorization. You should be able to just logic through all of this. Chemistry should involve a lot of initial studying to understand the logic, but once the logic is there, it should just be boom, 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 done, easy. Every chapter should be very easy once you get the logic. You can guess a lot of the trends, and you're right most of the time. You just got to remember the anomalies then. Cool. Hope this was helpful.